Let's do a share screen. This one, I think. Yeah, can you see my iPad? I can see it. Can you see it?
I can see.
Okay, so let's do a recap on what we had last time. We nearly finished, but we didn't really finish the discussion about black holes. So what did we do last time? We started from the Schwarzschild metric, right? Everything starts back from the Schwarzschild metric. ds squared is just minus 1 minus 2 gm over r times dt squared plus 1 minus 2 gm over r minus 1 dr squared plus r squared d omega squared. And then we start asking ourselves, okay, what would happen when we try to get to look at trajectories which go below this special radius, the Schwarzschild radius, or Schwarzschild is 2 gm. So what happens when we have a trajectory that goes there? Right. And then, you know, we realize that we have a problem, right? If we took it a new radial geodesic, right? That's what a light ray will do, right? A light ray goes over null, so that means ds squared is equal to 0. Radial mean d omega squared is equal to 0. And so we have 0 is equal to minus 1 minus 2 gm over r dt squared plus 1 minus 2 gm over r minus 1 dr squared. So we can just organize the cables here. So we can simply just put it straight away. We get dt over dr is equal plus minus 1 minus 2 gm over r minus 1. And we see that we run into a trouble, right? Because when r is very large, then dt over dr is equal to plus minus 1. So if we look at the light cone, right? So this is t and this is r. So if we look at the light cone of an object far away from this, let's make this special radius, 2 gm or c squared, right? Then the light cone would just be a plus minus 1, right? The photon, of course, travels on the light, and observer will travel somewhere in the middle. But as we get closer and closer to this special radius, then the t over the r will get us closer and closer to infinity, right? Especially it will go to infinity at this radius. So that means that the possible light cones will get narrower and narrower. Which means that in these coordinates, right, an observer will never be able to reach this special radius at the finite life, at the finite time. It's going to take an infinite amount of time to reach it, which is indeed true. From a point of view of an observer that sits at infinity, if there is an astronaut that decides to travel inside a black hole, right, and the astronaut signals to the observer, you know, at the spaceship, what's going on there, what am I seeing, I'm fine. And then, you know, what will happen is, as we discussed, right, as the astronaut approaches the black hole, then it will become redder and redder, of course, consistent with the gravitational redshift, and the signal will get slower and slower. And it will take an infinite amount of time for a signal from this radius to reach an observer at infinity, right? So in fact, we will never be able to see an astronaut falling into the black hole or any other object. It's just going to take us an infinite amount of time. But I said this is, in some basic sense, this is an artifact, because there's nothing special happening in the curvature of space-time at this location at this point. So from the astronaut point of view, from the local astronaut point of view, he will be able to cross that without even noticing. You won't even notice that anything special happens there. Right? We just, if we have some astronaut that decides to travel into the black hole, it will just proceed on to travel. Of course, we from infinity, right? We could just look at the signal from this astronaut is sending us, which will get, of course, redder and redder as the astronaut approaches, and we'll never see the astronaut really getting there, right? But we'll still get there. Now, so we wanted to see if there is another way of, reformulating the coordinates. If there is a way of reformulating the coordinates in such a way, and we started manipulating with the coordinates, right? So the first thing we did was defining the Tourtois coordinates. Which we obtained by simply integrating this equation. So these are equations in which r gets to minus infinity, essentially. So now we can reach there, but simply we put this r, the Schwarzschild radius, to minus infinity, right? So r star is just r plus 2gm ln of r over 2gm minus 1. Now, there is a subtle point here, which I think I haven't stressed it properly, right? Since t goes to infinity, right, in some sense, there is no point in defining these coordinates at r, which is smaller than 2gm, right? So when we put this absolute value, we are enabling it to be defined, but the physical meaning is not exactly clear what it means there. And then we can write down the metric using these coordinates. We see that the metric behaves nicely, which is what we wanted to have, right? So we had ds squared was written as 1 minus 2gm over r minus dt squared plus dr star squared plus r squared d omega squared, right? So everything is well behaved, but that's okay, doing something. And then the next step we did was to adapt the more natural coordinates, coordinates which more naturally adapt to x, which are the u tilde and v tilde, right? These are the coordinates which are 0 over null geodesics, t plus r star and t minus r star. And then we simply replace the coordinate t with the coordinate u tilde. So we have t was replaced with u tilde, and the result is called the Eddington-Finkelstein coordinates. Right, ds 2gm over r du tilde. Can you hear me? Squared plus du tilde dr plus dr du tilde plus r squared d omega squared. So we said there is no problem, right? The determinant of the metric g is just minus r to the 4 sine squared. And because of that, right, this enables us to extend the validity of these coordinates, not just to r equal to gm, but also to r equal to 0, right? So because we're now having a coordinate which is well behaved, doesn't go to infinity, then we can extend r, the validity of r from 2gm down to r equal to 0. Right, r greater than 0. Now, when we looked at geodesics, we find something interesting happening here, right? So the geodesic again, radial null curve, du tilde over dr is equal to 0 for infalling, namely decreasing r, and 2 times 1 minus 2 gm over r to the minus 1 for outgoing particle. And when we plot that, you see that there is something very interesting happening here. Right, so this is u tilde, and this is r. This is r equal to gm. So for infalling, the slope is 0. For outgoing, right, when r is very, very large, it will be 2. So it will be something like that. Right, this is the light cone, right? So if we are here, we can go anywhere within this light cone. Now, when we are approaching this special radius, right, the infalling is still 0, the outgoing becomes infinite. So now the light cone looks like that. And when we are inside, then the slope here becomes smaller than negative. So it will look something like that. And that is very interesting, because that means that when we are looking at it, it's the same metric, but using these different coordinates, we're seeing something very interesting happening here. An object, right, which is here, is free to go either towards the event horizon or away from the event horizon. But once the object crosses the event horizon, there's only one way it can go, right? All the future directions will always point towards decreasing r. So anything that will happen here, the information will propagate only in one direction, which is towards decreasing r, until we reach the singularity at r equal to 0. Which means that no event that takes place in this region of r smaller than 2 gm can ever be communicated to the outside world. So when we are an observer here, when we are looking and we try to get any information from anything that may happen, right, in this region here, r smaller than 2 gm, no information can reach us. Now, it does not mean that nothing happens there. Many things might be happening there. We don't know. Because any event that will take place here, right, all of its future directions will be pointing towards the singularity at r equal to 0. Right? Which means that we have no way of telling what will happen. So that's why this radius, the Schwarzschild radius 2 gm, has another very important name, which is called the event horizon. Right? In a very basic sense, this is the edge of the universe, if you want. This is the edge, beyond that, nothing that happens in this region can ever be communicated to the outside world. Okay, so that's the event horizon. And of course, from our perspective, when we're trying to see inside, right? When we're trying to have a look, we'll have a telescope that will look inside, right? We have a telescope that will try to see what happens. What will we see? Just a black region in the universe because nothing can get out of it. So we'll call it a black hole. Now, but I said that this is not the end of it, because it's actually getting more and more interesting, because we chose, when we constructed the Eddington-Finkelstein coordinates, we essentially did some mathematical manipulations. One of those was to choose, replace the time coordinate t with u tilde, which is especially fitted for infalling particle. But this was our choice, which broke the symmetry here. We could have chosen to replace t with a v tilde. And then we'd find out exactly the opposite, namely all future directions will take us outside. This will be called a white hole, if you want. Now, it can be quite confusing, but remember one thing, right? When we look in the regular coordinates that we used to think of, right? Then we said getting into the horizon, it means that t goes to plus infinity. So getting outside of the horizon means t goes to minus infinity, somewhere in the distant past. Now, of course, in the very, very far distant past, the Schwarzschild metric was not valid because the universe itself was not, we couldn't treat the universe as being empty with a single source of gravitation. So in some sense, it's really a mathematical manipulation, nothing more than that. But to see the full structure, we made somewhat more manipulations and we defined new coordinates, which were the Kruskal coordinates. And these are the coordinates that reveal the full mathematical structure of the Schwarzschild metric. So we call them U and V, where U is just R over 2 GM minus 1 to the power 1/2 e to the power 4 R over 4 GM, and then cosine hyperbolicus of t over 4 GM. And then V is equal R over 2 GM minus 1 to the power 1/2 e to the power R over 4 GM, and sine hyperbolicus of t over 4 GM. And we said that using these metrics, these coordinates, the Schwarzschild metric, can be written in a very nice form. ds squared is just 32 g cube m cube over r e minus r over 2 gm minus dv squared plus du squared plus r squared d omega squared. This is the same Schwarzschild metric, just written in different coordinates, these Kruskal coordinates. Right. Now the r is defined basically from these coordinates. So u squared minus v squared is equal to r over 2 gm minus 1 e to the power r over 2 gm. Now, obviously, in these coordinates, just looking at the metric, we have that dv over du is plus minus 1, which you can see from here. Now we said that in these coordinates, radial and null geodesics, ds equal to 0, d omega equal to 0, radial, null, geodesics, a curve. Right. This is just that v is equal plus minus u plus some constant. So exactly as they look in flat space. Right. So everywhere in these Kruskal coordinates, the light cone, regardless of where we are, the light cone will always look like exactly like they look in a Schwarzschild metric. Doesn't matter where we are. Now the horizon, okay, the horizon is r equal to gm, is defined as v is equal plus minus u from here. Now I was asked, that was my mistake, I didn't answer it right away. Why not simply put it u equal to 0 and v equal to 0? And the answer is simple, because then you have a 0 here indeed, but then you have an infinite in here because time is infinite. So it's a 0 times infinite, which is ill-defined. So the correct way to define the horizon is that u equal plus minus v equal plus minus u, meaning that it will look something like that. This is the horizon. Oh, sorry. So v equal plus u, v equal minus u, and at r is equal to gm, t is equal to infinity. Here it's r equal to gm, and t equal minus infinity. Now surfaces of constant radius, meaning that, so r constant, that means that u squared minus v squared is just some constant. Right? Which constant r would look something like that in these coordinates. The parabolas. Constant time, right, that's v over u, it just tangents the hyperbolicus of t over 4gm. So this is just straight lines, right, that all goes through the origin. So constant time would look something like that. Of course, this is t equal infinity, right? The singularity, right, is r equal to 0. So when r is equal to 0, that means that v squared minus u squared, or v squared is smaller than u squared plus 1. So you have it, u squared goes between minus infinity and plus infinity, and v squared has to be smaller than u squared plus 1. So the r equal to 0 surface is this. again, you cannot use this definition here, because if you say r equal to 0, you get some imaginary number. But again, this is a region that cannot be reached in the standard r and t coordinates because it requires t to be greater than infinity. So you cannot use directly this definition of u and v to infer the r equal to 0. Okay, so this diagram that I just drew, this is called Kruskal diagram for natural reasons. And it can be divided into 4 different regions, right? Region 1 is here, region 2 is here, region 3 is here, and region 4 is here. Right, the regions are separated by these u equal to v lines. So using this diagram, these coordinates, we can now get the full mathematical solution, right? So we are always in region 1, right? That's where we are. We are outside of the, this is me, right? Now, region 2, of course, we can travel, constant radius will take us, you can see, constant radius will take us in a hyperbola. Right. Now we can travel, in all future directions can take us into region 2. Once we cross this line here, of course, then we're entering the black hole. Now from here, it is clear from this diagram, right, that once we cross that, then all future directions will necessarily take us into the singularity, namely at r equal to 0. So again, that is quite important. So once you cross the horizon, the event horizon, it's not that you cannot come back. You cannot even stay at the same radius. You will slip down right to the singularity. Of course, if you try to avoid it by making anything, it's just going to be faster because the longest time it's going to take is along the geodesics. So if you were stupid enough to cross the horizon, you better do nothing and wait until you reach singularity. One day you'll die and nobody's going to be able to tell what happened to you because nobody from the outside world could, you could not communicate with them anymore. So this is, of course, the black hole. So region 2 is the black hole, right? Region 3, we said this is the white hole. So in some sense, it's the opposite to a black hole, right? If there is anything there, then all future directions, right, will take it outside of this region. But it's really a mathematical artifact, right? Because it refers to things that happen at t equal to minus infinity. And at t equal to minus infinity, the Schwarzschild metric was not a valid metric. And this is actually, we're going to start discussing it today, shortly. So it's really, there is nothing really there, right? From a mathematical perspective, there is, but from a physical perspective, there isn't really anything because it requires t to be equal to minus infinity and the Schwarzschild metric to be valid at that time, right? Which is not. Which leave us with this region 4. What is region 4? What is region 4? Come on, any ideas? Any ideas, guys? Yeah. Somebody? What happened? Yeah, what is this region 4, guys? Some idea? Come on. How many of you have seen science fiction movies? Some do, right? But it appears there, right? That is some sort of a parallel universe to ours, right? This is a region which is asymptotically flat, right? And we cannot reach it unless we can travel at space like geodesics, namely faster than the speed of light. That's all these science fiction ideas of wormholes or something like that that will take you through to an parallel universe. That's where it's come from, right? Cool, isn't it? So it's mathematically there. There is no way for it to communicate with us, of course, right? Unless there is some sort of a configuration that can join, this real space with this imaginary real space here, right? There's this imaginary space in region 4. That's the parallel universe. Cool, isn't it? Okay. So we pretty much completed the discussion I want to have about the Schwarzschild metric. Just one last point, which is kind of an important, right? So after getting this, from science fiction back to science, black holes in nature. How do we have black holes? Did we see black holes?
We think we did.
Yeah, we did. We see the shadow of black holes, and we have indirect evidence for their existence for many years now. There was a Nobel Prize this year, right? For the black hole at the center of our galaxy. It was just this year was given to 3 guys.
Asaf, I have a question regarding black holes, because before we continue.
Yeah.
So we arrived to black hole via the Schwarzschild solution, and it's very complicated. But in general, you can imagine maybe you have just a massive, massive object which light can go out, which is not singularity or anything like this. Just you can, it's so massive that light cannot escape or something.
You mean that they escape? You're talking about the classical black hole.
Exactly, yeah, like a classical.
This was suggested by Poincaré, I think, back in the 18th or 19th century. Sorry, it has to be 19 because once you realize, that's true, once you realize that the speed of light is finite, and you know that the escape velocity, the classical escape velocity, right, is...
it's not really classical because you do need to assume that light is affected by gravity, so it's need the general relativity.
No. Again. Once you realize that the speed of light is finite, light cannot travel any faster than something. And once you know that the classical, right, Newtonian mechanics, escape velocity, right, depends on the mass. A heavier object requires a faster escape velocity. Then you can envision a situation where an object is so massive that, that the escape velocity from this object is faster than the speed of light, right? I guess that's what we're referring to. But note that there is a huge difference here. Because the escape velocity, normally we talk about the initial velocity that we need to give to an object in order to escape it, right? So, if I'm throwing a stone, I have to give it, I don't remember the exact value, right? 40,000 or, I don't remember the value, right? You can calculate what is the initial speed I need to give the stone in order for it to fly out to infinity and escape the gravitational pull of Earth, right? But, in Newtonian mechanics, right, I can use an acceleration, right? I can throw a stone, but it's not a stone, like a rocket, right, which continues to accelerate and builds up the speed as I'm getting away from the gravitational potential. I have stage 1, which gives me some velocity and some height, and then stage 2, which gives me another velocity, and there's stage 3. Eventually, people manage to get to the moon, right? Of course, in GR, you cannot do that. The space-time is curved, right? Even if I accelerate, this is the key figure here. All future directions of any event that happens inside the event horizon, even if it is being accelerated, it doesn't matter. All future directions will always point toward the singularity. This is something which is, again, it's completely GR. Again, that's why this picture is actually a quite good picture, like a funnel, right? That goes in. So, to climb out, let's say that the Schwarzschild radius will be this one, right? So as long as you're here, you can still climb out. But once you're here, in order to climb out, you need to travel faster than the speed of light, which is impossible. So the only thing you can do is just spiral inward. And that picture is very different than a classical picture.
Okay, thanks.
Right? Okay. So black holes in nature. So there are black holes in nature. We have seen them. We've seen evidence for them. We've even seen image of a black hole. And we have many indirect images that show that black holes exist, including at the center of our galaxy. We believe that at the center of any galaxy. How are black holes formed in nature? Just kind of very briefly, 5 minutes from the course in astrophysics. So the starting point is the sun, right? How is the sun working? The sun is in a steady state, right? What happens in the sun?
Nuclear reaction.
Right. So why is the sun? The sun is so steady, right? And it's been like that for billions of years. Otherwise, life here could not be developed. What caused the sun to be in a steady state? It's not changing, right? The luminosity is fixed, the size of the sun is fixed, and it's been like that for billions of years. Why is that?
Because the radiation outwards counteract the gravity inwards.
Exactly. So the life of the sun and the life of every star, right? It's a steady state, right? There is a pull of gravity, right? So you have a gravity that pulls the sun. That's a gravity pull. Gravity pulls inward. But in the center of the sun, there is a nuclear burning, which produces photons. And it's actually these photons that push the sun back, that pushes outward. It's the what's called the radiation pressure, right? Photon carry momentum. So there's a pressure. So it's called the radiative pressure. I can't even see that. Yeah. Radiative pressure. Now it's been like that for something like 4 billion years. It will keep like that for another 4.5 billion years or so. Until what happens?
Becomes a red giant.
To what?
Becomes a red giant.
No. What will happen at the end?
It'll collapse indoors.
Wait, why? Why would it collapse? Because
the nuclear source will
simply run out of fuel. There's no more fuel, then it collapses. Right? It will go through a stage of a red giant first. That's true. So run out of fuel, so no more fuel. Until no more fuel. And when there is no more fuel, then that's it. It starts to collide. It will first expand, but that depends on the different reactions that happen inside. But then it will start shrinking because there will not be any balance anymore between the radiation and the gravity. It will shrink until what? Until when? Will it shrink forever? No more fuel, no more photons produced counterbalance gravity. So until when will it shrink?
Pauli restrictions.
Sorry?
Pauli restrictions.
Pauli, right. You all heard of Pauli exclusion principle, right? What will happen is that it will shrink, the electrons will get closer and closer together, right? But there is a Pauli, do you know of Pauli exclusion principle? That's a second or third year quantum mechanics. Yeah, you know, right? Yeah, at least some of you know, right? So Pauli exclusion principle, you cannot have two electrons at the same state, right? So that will prevent from further shrinking. And then how we call the star until the star will shrink, compress is the right word, not shrink. Will compress, electrons will get closer together. And stopped by Pauli's exclusion principle. Right? Because electrons are fermions and fermions obey Pauli, and then they cannot be in this state. Right? You know that. How do we call such a star?
White dwarf.
Yeah, let's call it white dwarf. This is going to be the end life of our sun, white dwarf. Now we're seeing many of these stars. It's kind of a dead stars. There's no more fuel. They just keep on radiating slowly, and cooling slowly, dissolving into infinity.
שאלה בבקשה.
כן.
למה כדור הארץ לא ממשיך להתכווץ?
כדור הארץ?
כן.
You mean why is the Earth not shrinking?
Yes. הרי יש לנו את הגרביטציה, אין לנו לחצים מבפנים החוצה.
No. The Earth, well, the Earth is pretty far from that because gravity of the Earth is very, very weak. Remember that gravity is the weakest force there is. Essentially, the answer to your question is why isn't the Earth shrinking is because of electromagnetic forces, right? Electromagnetic forces are the forces that bind molecules together. Right? And these are the forces that make solids, and these are the forces that make liquids, and these are the forces that make gases. And these are much, much stronger than gravity. So while the gravity acts to contract the Earth, the electromagnetic forces are strong enough to prevent the Earth from being shrinking more, simply because they make liquids and solids. If you try to compress a gas, you can compress it up to a liquid, but then if you try to compress further a liquid, it's going to be very, very difficult. Okay. So if we go back to the essence of these things, it is because of electromagnetic forces. And of course, in the center of the Earth, it's all liquidified. Magma. For the sun, right, the gravity of the sun is way, way, way bigger. So simply because there's no mass, the mass is much bigger. And so it overcomes the electrostatic forces at the center of the sun. Of course, not at the outskirt of the sun.
Yeah.
All right. Any more questions about that? Okay, so that's for the sun. We have, what if we have stars that are bigger than the sun, more massive than the sun? Then what happens when these stars complete their fuel? But if a star is more massive than, roughly 1 point something, 1.5 the solar mass, then the effect of gravity is going to be even stronger. And then the electrons, the Pauli exclusion principle will not be enough, the electrons, to stop from collapsing. Then what will happen?
Eventually, helium flash.
What? No. What will happen to the star? No helium flash. For helium flash, you need to have a helium.
Neutron Star.
Neutron star, right? What will happen is that the electrons and protons will merge together into neutrons, right? It will keep on collapsing, and the electrons will collide with the protons, getting what's called a phase transition, ending up with the neutrons. So for more massive stars, a more massive star will keep on collapsing until electrons will recombine with protons to form a neutron star.
But Asaf,
Yeah.
when we say that we are out of fuel, we
Yeah.
mean we are out of atoms of helium. But actually,
It's a bit more complicated.
hydrogen convert to helium.
Mostly, yes, but that's not the only thing that happens. There are several other processes that happen there.
Fine, but so why doesn't continue to be converted to other heavier atoms?
It will be continued. That's exactly the stage. I didn't want to get into that. Continue to convert to heavier atoms. That is the stage where the star becomes a red giant. Then you have the Cno cycle. You get carbon, nitrogen, oxygen. That's how the elements are being formed, essentially. You can get that up to iron. Because the iron, if you look at the table, the iron has the lowest binding energy. So you cannot go beyond that. Beyond that, it has to be a transient. A transition means in an explosion, which is in a supernova. Once you reach that, there is no more way of extracting energy. You cannot get more energy. You gain energy by converting hydrogen into helium, but you cannot gain more energy after you reach iron. Okay, so I figure this is not really the part of this course. This is more in the astrophysics course, right? You can produce all the elements up to iron within the cores of stars under certain conditions, who, to be fully honest, are still nobody fully sure about. A star may explode, releasing these elements. These are the elements that we are made of, essentially. Right? And the abundances of these elements, the rate in which they're produced in the stars are the same as the abundances that we're seeing them on Earth. And that's why we believe that the same elements exist everywhere. So thinking about the possibility of having oxygen in other planets and water in other planets, they are very high, because these elements are very abundant all over. Okay, but that's a little bit outside the scope of this course. It's more in the astrophysics course. Now, a neutron star, as it forms, that's where some of the neutron stars will explode, and you end up with a supernova. But the end result is a neutron star. Neutron star has other names that you might hear of: pulsars or neutron stars, etc. But this is also limited by how much mass you start with. If you start from too much or more than a certain value, the exact value is uncertain, because we don't really sure about all the processes that happens when the star explodes. Then what will happen? If you start with mass which is too much than even the neutrons the general pressure can handle, then you end up with nothing can prevent further collapse, and then you end up with a black hole. Right? So we believe that there are black holes for masses which start from a few times the solar masses upward. And we have seen those, we've seen evidence for those in gravitational wave detectors in the last few years. We have seen indirect evidence for those in the last 20 or so years by looking at the accretion, the method that accretes into this black hole, is called X-ray emitting binaries. All right, more mass, more initial mass. By the way, I don't know if you think of it, but the neutron star is just a huge atom. Then you end up with collapse into a black hole. Questions? Really good atom. Any questions? No? This was supposed to be just a quick recap, but it ended up taking a full hour, which is more than I thought, but okay. Any more questions? Because we're going to a new subject. No? Okay. So I told you that there are various solutions to Einstein's equation. We thoroughly discussed one, which is the Schwarzschild, which describes black hole. I did mention, I didn't say anything about it really, but I did mention that there are two extensions of the Schwarzschild metric. One to a metric that includes charges. That's called the Nordstrom. I always forget. One is Nordstrom and the other one is Razor Nordstrom metric. That includes charges, and the one that includes rotation. So angular momentum, which is non-zero. That's called the Kerr. For practical reasons, there are good reasons to believe that if there is any charge, then it will discharge right away. So in reality, we do expect to see Kerr black holes, and this is indeed what we saw in the Event Horizon Telescope. Okay, that's enough for this description. Now we're going to the next part of this course, which is called Cosmology. So, so far, we applied a solution to Einstein's equation in vacuum, right? R mu nu is equal to 0. Now we would like to apply Einstein's equation to study the entire universe. Of course, the entire universe is not empty. We live in it. So we cannot say that it is 0, it is not. So we can say the right-hand side of Einstein's equation, we cannot put it to 0 because it is not. Now, the study of the global properties of the universe is called cosmology. And this is a distinctive subject from astronomy. Right? When we speak about astronomy, often, or astrophysics, right? Often astrophysicists treat specific objects, like study black holes, study stars, study exploding stars, like supernova, neutron stars, white dwarfs, etc. Some study structures like galaxies, etc. Cosmology is the study of the universe as a subject, as a whole, right? The global properties. And again, the starting point is a solution to Einstein's equation. That's where it all starts. Now, the modern day cosmology is based on what's called the Copernican principle, which says what? What did Copernicus say? What was Copernicus' main contribution to mankind, which was a huge contribution? What did Copernicus say?
The Earth revolves around the sun.
Right. In other words, Copernicus said, look, we are not at the center of the universe. Right? Until Copernican times, people believed or wanted to believe, and actually many believed, that we are at the center of the universe and everything rotates around us. Somehow some people still believe like that today, but no, we're not. So after Copernicus, we say that there is nothing special in when we are in the universe. We are just one object out of very, very many objects in the universe. So the Copernican principle basically states that the universe on large scale is homogeneous and isotropic. So modern cosmology assume that the universe is homogeneous and isotropic. Right. Now combined together, these are called the cosmological principle. Now, what does it mean homogeneous? Just to get clear, just to get things straight up. When I say that something is homogeneous, what do I mean? Come on, guys. What is homogeneous?
It's the same everywhere.
Right, right. The properties are the same everywhere. Or in other words, we can say that the universe is invariant under translations. Right? We want to be somewhat more mathematical. The universe is invariant under translations. And when we say isotropic,
it's independent on the direction.
right, right. It looks the same in each direction. Properties, the properties look the same in all directions. Or again, in a mathematical way, we'd say that the universe is invariant under what?
Rotation.
Of course. Thank you. So we said that this is essentially a modern version of this Copernican principle, right? Copernican principle, which essentially states that, no, unfortunately, we are not at the center of the universe. Now, it's immediately to see that these assumptions are simply incorrect. I mean, when I say the universe is homogeneous, means it's the same everywhere. But obviously, the conditions here and the conditions at the center of the sun are not the same, fortunately. Right? Also, the assumption of isotropic is incorrect, right? Because if I look to my left and if I look to my right, I don't see the same thing. The world does not look exactly the same in all directions, right? So, obviously, it's kind of fun to see, but, immediately we can tell that this is not right. But we believe, and we have good reasons to believe, that when we look on a large enough scale, this is correct. Now, when I say large enough scale, of course, it's not the scale of the Earth, it's not the scale of the solar system, it's not even the scale of the galaxy, right? It's scales which are much larger than that, right? So I should say that these two assumptions are believed to be correct, but only on a very, very large scale, right? Scales which are much greater than a galaxy. Right? These assumptions are believed, not just believed to be correct on a very large scale. Right? We see that when we look at the number counts of galaxies, right? When we have galactic surveys, very far away from the local cluster of galaxies, and number counts of galaxies. When when we're looking at the observational diffusive X-ray and gamma ray background, and most importantly, what is the best evidence we have for this homogeneity and isotropicity? That's something I would expect at least one of you to tell. What would that be? Yeah? Yeah, guys. No clue?
So what was the question?
What would be indication for the universe is homogeneous and isotropic on the large scale?
Maybe the 3 degrees Kelvin.
The what?
3 degrees
Yeah.
Kelvin.
CMB. Thank you. Yeah, that's the correct answer. Cosmic microwave maker. We'll return to that. Cosmic microwave background. It's a 2.7 degrees Kelvin, which is everywhere surrounding us. Now we do see fluctuations. I don't know if we'll have much time to discuss these fluctuations in the CMB, but it's they're very small. It's the order of 10 to the minus 5, so we don't really need to worry about it. Now, okay, just formality, right? So when we say homogeneity, right, we mean that between any 2 points on the manifold, P and Q, there is isometry, right? We talk about isometry in this course, right? We did, right? I think I did. So homogeneity means that there is an isometry between every 2 points, P and Q, on a manifold. Now, just one thing, right? Know that the metric can be homogeneous, but it can be isotropic, but not homogeneous. Right? Can you tell me a metric that is isotropic, but not homogeneous?
Maybe polar coordinates?
What? What did you say?
Polar, you can't have translation, but you can have rotation.
No, nothing to do with coordinates. I'm talking about the manifold. Coordinates, remember, is something external. We put it. Change the pole, put the pole somewhere else. We choose to put the poles on the north, south, and north. We can put it in the east and west. A cone, right? A cone is a homogeneous space, isotropic space. If you're standing here on the apex of the cone, right? Everything looks isotropic, but of course it's not homogeneous. Now you can also have a situation where you have a space that is, homogeneous but not isotropic. You have something like field that goes like that. It's homogeneous, but not isotropic. But if it's isotropic everywhere it must be isotropic. Isotropic everywhere. It has to be isotropic, also homogeneous. And if it is isotropic, if it's homogeneous and isotropic around one point, it also has to be isotropic around everything. Homogeneous and isotropic around one point. That means it's isotropic everywhere. So, think of it for a little bit. Now, of course, we cannot really tell much about the homogeneity in the universe because we're only at one point, but we have many evidence for isotropy of the universe. Right? So, the Copernican Principle will tell us that the universe is also homogeneous. Now, how do we call a space that is both homogeneous and isotropic? This has a mathematical name. A space that goes homogeneous and isotropic is called maximally symmetric. Maximally symmetric space. Okay, so we're going to study now maximally symmetric spaces, but there is one thing which is important for us in this context. When we go back nearly 100 years ago, Edwin Hubble showed that the universe is actually expanding, right? Which means that when we speak about maximally symmetric, we are only talking about the spatial part of the universe, not about the temporal part, because the temporal part is changing, right? Changing with time. So there is some small subtlety here because you can think of the spatial part of the four-dimensional space-time is really a subspace of this four-dimensional space. So what we're really talking about here is a space which is a maximally symmetric subspace. Okay, and the metric that we're going to derive, this is called the Robertson-Walker metric, is exactly the metric that will describe that, namely a metric which is can represent a space with a maximally symmetric subspace. Okay, a metric which describes space maximally symmetric subspace. This is the Robertson-Walker metric. It was derived in the 1920s. And the first task we're going to do is to derive this metric. Now, remember, this is a different metric than the Schwarzschild metric because it will describe the universe. Namely, it is not a vacuum solution to Einstein's equation. It is a solution to Einstein's equation with matter in the universe, right? Because the universe contains matter, under the assumption that the spatial part of the metric is homogeneous and isotropic. Okay? So don't get confused by that and the Schwarzschild metric. Questions? Questions? No? No. Okay. So before we can actually do the derivation, well, it's not going to be a very difficult derivation, certainly not relative to the things we already did in this course. But we still need to do some mathematical manipulations. So let's start doing them now. So some mathematical structure of maximally symmetric spaces. So formally, or mathematically, right, the maximally symmetric space is a space that have the maximum number or the largest possible number of Killing vectors, right? This statement is not really going to surprise you, right? So formally, a maximally symmetric space possesses the largest number of Killing vectors. How many Killing vectors, maximum number of Killing vectors we can have on an n-dimensional manifold? How many Killing vectors we can have? Maximum number?
Like n plus 1 over 2. What?
Right. Maximum number of Killing vectors is n times n plus 1 over 2. Now, okay, I'm not going to give you a full proof of that. We can, but there's no need. You can simply imagine, you know, Minkowski space as an example of a maximally symmetric space, right? So any you know, Euclidean space of Rn. Right? So it's more an example than a real proof, a full mathematical proof, but that's enough to tell you, to give you the idea, right? So we have on Rn, we have n translations, and you know, one for each of the directions, and then we have n times n minus 1 over 2 rotations. Okay. Because for each of the n directions, there is an n minus 1 direction which we can rotate it into. Right? So, but of course we have to divide by 2 for not overcount. Because rotating x into y is the same as rotating y into x. So total we have n plus n minus 1 over 2 times n, which is just n times n plus 1 over 2. Independent Killing vectors. And you saw that, right, in your homework. So, you know, the same argument would hold for, you know, any space, maximally symmetric space with a curvature, which is essentially an n-dimensional space. Right. That means that when n is greater than 2 or equal to 2, there is some noise there. I don't know where it's coming from. Is it okay now? Can you hear me, guys? Yeah, okay. Where n is greater than or equal to 2, right? That means that there are more Killing vectors than dimensions. Right? Right. Remember, this sounds like a bit confusing because at a given point there is at most n independent killing vectors, but the killing vectors are defined over all space. So when you look at the entire space, you end up with n times n plus 1 over 2 independent killing vectors. Okay. Now, in order to proceed, what we need to do is to get a few more algebraic properties of killing vectors. It's a bit, I don't really like these algebraic manipulations because they're just algebra, and there is some chance that I make a mistake. But let's hope I do not. And if you get confused, just remember that I need this algebra to get some results. So I'm going to derive now a result which is going to be needed. So what I'm going to do now is to look at a few properties, algebraic properties of killing vectors, which we did not discuss before because there was no need, but now we actually do need to discuss them. So a few more algebraic properties of killing vectors. Okay, these are something again which we're going to need them, so I'm grabbing them now. So remember that the killing vectors would satisfy the killing equation. Let's switch color, right? So killing equation K sigma rho plus K rho sigma is equal to 0, right? Now, remember that when we discussed the curvature tensor, we saw that when you take the commutator of a vector, right, it is the vector times the curvature. So in other words, we had the K sigma rho, say mu minus K sigma mu rho, right? This is just equal to nabla rho, commuting with nabla mu K sigma, right? This is just equal to minus R lambda sigma rho mu K lambda. Right? Remember, we derived this equation when we did the curvature. This is true for any vector, not necessarily a killing vector. In general property of the Riemann. Right? That's true for any vector. So specifically, this is also true for a killing vector. And we also had the cyclic sum rule for the curvature tensor. So plus cyclic sum rule. Namely R lambda sigma rho mu plus R lambda mu sigma rho plus R lambda rho mu sigma is equal to 0. We had that as well. So again, these are properties which we derive with the curvature. Now, okay, so let's use these two together, and we find that for any vector, not necessarily a killing vector, right? I just add up all these, and we find out that K sigma rho mu minus K sigma mu rho plus now the cyclic sum, so plus K mu sigma rho minus K mu rho sigma plus K rho mu sigma minus K rho sigma mu is equal to 0. Okay. Now I can use the killing condition. So far, this is true in general, right? This just follows from the properties of the Riemann. Now I can use again the properties of the killing equation, but again, that's the first time I'm actually using it. On that equation, so I can switch down like minus k rho sigma mu is a plus k sigma rho mu, right? For example, I take that. Well, this is a plus k sigma rho mu from the killing condition. So, and then the same I can do with the other minuses. So combined together, we end up with a k sigma rho mu minus k sigma mu rho minus k mu rho sigma is equal to 0. Okay, just use the killing condition here. And then I can use that again with this equation here. Combine it with this one. Write down k mu and k mu derivative with rho derivative with sigma is just a minus r lambda sigma rho mu k lambda. Okay, it's again just algebra, so a little bit annoying, but not too much. And then I can again use the definition of the curvature and write down the commutator of two covariant derivatives of this, right? Again, it's the same definition that we had here, but now for k mu rho. So we have it out as k rho mu sigma, and then derivative with respect to nu, let's say minus k rho mu, now mu sigma. This would just be minus r lambda rho sigma mu k lambda mu minus r lambda mu sigma mu k rho lambda. Right. So the next thing we need to do, right, so we have these two equations. And now I just take the derivative of this one and plug it in here. And we end up with r lambda sigma rho mu k lambda mu minus r lambda mu rho mu k lambda sigma plus r lambda sigma rho mu derivative is mu minus r lambda mu rho mu derivative with sigma. This is multiplied by k. This is multiplied by k lambda is equal to what we had in the right-hand side, minus r lambda rho sigma nu k lambda mu minus r lambda mu sigma nu k rho lambda. Essentially, what I did here is to take this equation and then simply replace mu with a rho and sigma with a nu. Take the derivative and plug it into what we have here. Plug it into this equation. That's all. So just follow the algebra, it's pretty straightforward. So now we can use again the killing condition, right? So in the killing condition, for example, we can replace K rho lambda with minus K lambda rho using the killing condition. And then the same we can do in second term here, minus K sigma lambda. And so we end up, and also in the first term, I see, minus K mu lambda. And so we end up getting minus R lambda sigma rho sigma mu delta kappa mu plus R lambda mu sigma mu delta kappa rho minus R lambda sigma rho mu delta kappa mu plus R lambda mu rho mu delta kappa sigma multiplied by K lambda kappa is equal to whatever is left here, like R lambda sigma rho mu minus R lambda mu rho mu sigma multiplied by K lambda. Oops. Okay. Now, crap, we're already over time. Okay, so this is the equation which we derived. It's again, I told you, it's a bit annoying. I don't like all these indices, but it's straightforward. We're sort of 2/3 of the way, no, maybe halfway towards the result that we actually need. So this is the result which we will use next time in order to get a specific form of what I'm really after is the specific form of the curvature tensor in a maximally symmetric space, which will enable us to derive this Robertson Walker metric. So since we're already over time, I suggest that I stop here and I'll just complete this derivative on Thursday. Any questions?
תודה רבה.
בבקשה. Any questions further? No. And if not, then I'll stop my sharing and I'll stop my recording.